Hi, my name is Shahnawaz. In this lecture, we will discuss that the various forms of compactness are equivalent when the space is given to be metrizable. But before that, we'll prove a short lemma. So let X be a sequentially compact metrizable space. So we are given that the X is a sequentially compact space, metrizable space. Then for any epsilon positive, uh, X can always be covered by finitely many open balls. Then X can be covered by finitely many open epsilon balls. So let us prove this. So we are given that the space is sequentially compact and metrizable, and we had to prove if we choose any epsilon, then this X can be covered by finitely many open epsilon balls. So we assume on contrary that there is an epsilon such that X cannot be covered by finitely many epsilon balls, and we will derive a contradiction. So assume on contrary that uh, there is an epsilon positive such that X cannot be covered by finitely many open epsilon balls. This is what we'll assume. Now, what we do, we'll construct a sequence as follows. So now construct a sequence, say xn, where this n is a natural number, as follows. So what we do, we choose x1, I mean the first term of this sequence in x arbitrary. So choose x1 belongs to x. So this x1 is any point in the space. Now for the second term of the sequence, now we had construct a sequence in x as follows. So now uh, so first one can note that if we take this set x and we set minus this set x with this ball be centered at x1 and radius epsilon, so this is non-empty. Otherwise if this is empty, then this single ball will cover x, and that is against our hypothesis, because we assume that this x cannot be covered by finitely many epsilon balls. So this is our hypothesis. So So this cannot be empty, otherwise X is covered by the single epsilon ball. By the single epsilon ball centered at X and not X, X1 and radius epsilon. So if this set is non-empty, we can pick a point, say x2 in the set. So choose x2 in the set x, which is not in the ball, set at x1 and radius epsilon. Similarly, we can choose uh, x3, which is in x but not in the ball. So similarly, we can choose x3 in the set uh, x set minus the union of balls bx1 epsilon and bx2 epsilon. So one can again note here that this set is non-empty, otherwise this x is covered by these two balls, and which is again not possible. So we can choose x3 in this set. So one can write the reason here, since this set x minus b x1 epsilon union b x2 epsilon is non-empty. So using the fact that x is not covered by finitely many epsilon balls, we get a sequence in this way. So using the fact that x is not covered by finitely many epsilon balls, so we get a sequence of points x1 x2 x3 so on in x. So the situation is like this here. So what we do, suppose this is the set x, now we choose randomly a point, say x1 here, and we draw a small epsilon ball over here. So this is the ball centered at x1 and radius epsilon. So one can note here, this epsilon ball cannot cover the whole x, because that would be against our hypothesis. So there is a room more to choose a point from x which is not in the ball. So let us pick say a point here. Let us call this point x2. So this x2 is in the set x but outside the ball centered at x. Now what we do, we choose a ball centered at x2 and radius epsilon. So sorry, this is like this. So we take the radius epsilon. So it is like this. So this is the ball centered at x2 and radius epsilon. Now we choose x3 somewhere here, outside the ball. I mean outside the ball, outside the union of these two balls. So that means the distance from this point x3 to x1 is bigger than or equal to epsilon, and similarly the distance of x3 from x2 is bigger than or equal to epsilon. And we draw a ball of radius epsilon around this x3. So we can pick infinitely many such balls, because uh, x cannot be covered by finitely many balls. So if this is the case, if we can pick such balls in finitely many times, then for each ball we pick its center, and by choosing by choosing the centers of these balls, we get a sequence of points in x. Now what is special about the sequence? So if we choose any two terms in this sequence, their distance, I mean the distance between these two terms will be bigger or equal to epsilon, because that is how we gonna structure this sequence. Now note that distance between xi and xj is bigger or equal to epsilon for all I not equal to j. So one can note over here, if we pick x1 and x2. So since this distance is epsilon and we chose x2 outside this ball, so the distance between these 2 points is going to be bigger or equal epsilon. So if this is the case, if uh, any 2 points in this sequence, I mean their distance is bigger than or equal to epsilon, so this sequence cannot have a subsequence which is, I mean, so let us write this down here. So therefore in this sequence, uh, x n, where n is n, cannot have a convergent subsequence. The reason is this: for a convergent sequence, and the distance between two consecutive terms becomes arbitrarily small. I mean, we can make distance smaller than any pre-assigned real number, say epsilon. But here, in this case, the distance between any two distinct terms is bigger or equal to epsilon. So if this is the case, this sequence cannot have convergent subsequence. This contradicts the fact that X is sequentially compact. So this contradicts the fact that X is sequentially compact. So hence our hypothesis is wrong. That means for any epsilon positive, we can cover X by finitely many open epsilon balls. So hence this considers the fact that X is sequentially compact. So hence X can be covered by open epsilon balls for any epsilon bigger than 0. Now, let us prove a general result. I mean, a result when we suppose our space is metrizable. Uh, then the various forms of compactness are equivalent. So this is the theorem. So let X be a metrizable space, then the following are equivalent. So first item is X is compact. The second item is X is limit point compact. X is limit point compact. And finally, X is sequentially compact. Let us prove this result. So first implies second is proved in the last lecture, and we do not need the metrizability there. So we have already proved that item first implies item second, and one can note here that while proving first implies second, we didn't use the metrizability of space X. So uh, if X ceases to be metrizable, even then and the compactness of X implies limit point compactness of X. So while proving first implies second, we do not need metrizability. However, while proving other two things, I mean, while proving second implies third and third implies first, we require the metrizability of X. So we have already proved. Let us make it clear here. We proved this in last lecture. Now to prove second implies third, I mean, we have to assume that X is limit point compact, and we are going to prove X is sequentially compact. So what we assume? We assume so. This is second implies third. So assume that X is limit point compact. Uh, then every infinite subset of X has a limit point. Then every infinite subset of X has a limit point. Hmm. It has a limit point in X. Now let us consider a sequence. So um, let Xn, where n is in n, be a sequence of points in X. Now, what we had to prove? We had to prove X is sequentially compact. So we had to prove every sequence of points in X has a convergent subsequence. So that means for this sequence, we had to prove it has a convergent subsequence. So if this is a sequence, let us take the set A, which contain the terms of this sequence. So let A be the set of terms of the sequence while n is in n. So now there are two possibilities. A can be either finite or infinite. So if the sequence is like this, say 1 0 1 0, so this is our sequence. So this is 1 0 1 0 1 0, so on. Then the set A will be the set of terms of this sequence. Since this sequence is in only two terms, 1 and 0, which are uh, repeating, so this set A consists of um, only two pointers. So that means when A is finite, then uh, uh, there is some point in the sequence which is uh, which is repeated infinitely many times, or we can choose this sequence, say uh, xn is a sequence of pointers consisting of 1 2 3 3 3 3, so on. So if in this case the set A will consist 3 points, 1 2 and 3. So again A is finite set. So that means when A is finite, then there is one point among these 3 pointers which is repeated infinitely many times. So one can note here 1 and 2, they are not repeated infinitely many times. However, the point 3 um, is repeated infinitely many times in the sequence. So if A is finite, uh, then there is a point x in X. Then there's a point x in A such that this x is xn for all, for infinitely many matrices of n, for infinitely many values of n. So hence in this case, so hence in this case the sequence xn has a constant, has a subsequence that is constant, has a subsequence that is constant, and we know the constant sequence converges trivially, and therefore converges trivially. So one can note here this sequence over here, this has this subsequence 1 1 1 1. So this is a subsequence of this sequence which is constant, and this constant sequence converges to 1. So that means this sequence has a convergent subsequence, and in this case the subsequence is 3 3 3 and so on. So again this sequence has a convergent subsequence. Now assume that now suppose that this A is infinite set. So on the other hand, let A be an infinite set. So now using limit point compactness here, then the set A has a limit point. So by limit point compactness of X, the set A has a limit point. This set A has a limit point, say X. Say X. Now we'll cook up a subsequence of the sequence xn that converts to x as follows. So now we cook up a subsequence of xn that converges to uh, x as follows. So first we choose n1 in, first we choose n1 a natural number in n, so that x n1 is in the ball center at x and radius 1. Now choose n2 in n such that x n2 is in the ball centered at x and radius half. So we can continue this process indefinitely, since each open ball centered at x contains infinitely many points of the sequence, because this x is limit point of the sequence. So since x is the limit of the since x is the limit point of the set A, any ball centered at x consists consists uh, consists at least one point of A different from x. So we can continue this process indefinitely. So hence we can continue hence we can continue the process of choosing the pointers x and I in the ball centered at x and radius 1 over I indefinitely. So we have a subsequence So we have a sub sequence x and I, where I is a natural number of xn. So since we can continue this process indefinitely, this means this any ball centered at x uh, consists at least one point of the subsequence. That means this subsequence converges to the point x. So hence, so one can note here what we do actually here. So if this is the set x and this is the point x, first what we do, we choose, if we choose a ball around this point, say this is the ball centered at x and radius 1. So what we do, we choose a point, say x, and so this is, so we choose a ball, we choose a point x and 1 in this ball. So since x1 is in the ball, so it is distance from x is less than 1, so this is, the ball is radius 1. Now what we do, we choose another point, um, x and 2 in the ball centered at x and radius half. So we pick another ball over here whose radius is half, and we pick a point x and 2 here, and find, and then we pick a ball of radius centered at x and radius 1/3, and we pick a point x and 3, and the process goes on. So that means, so why this process can be I mean, why this process cannot terminate? And the reason is that this x is the limit point of the set A, and that means any ball centered at x must contain a point of A um, different from x. So, so this shows that the sequence x and I converges to x. Hence, x is sequentially compact. So one can note here why this sequence converges to x, because uh, any ball centered at x uh, contains a point of the sequence different from this x. That is the reason this sequence subsequence converges to x. So this proves the sequential compactness of x. Now finally we assume we are going to prove third implies first. I mean, we assume x is sequentially compact and we prove x is compact. So assume x is sequentially compact. So we wish to prove x is compact. We wish to prove x is compact. That means we had to prove any open cover of x exhibits a finite subcover. So let us pick an open cover of x. So let this fancy A be an open uh, cover of X. Now, since X is sequentially compact, then the open cover A has a Lebesgue number, say delta. So we know a sequentially compact metrizable space satisfies that Lebesgue number lemma. So now we are given X, which is sequentially compact and metrizable. So for this open cover A of X, so this open cover A satisfies the Lebesgue number lemma. That means there is, so since X is sequentially compact and metrizable, therefore the open cover is fancy A has a Lebesgue number, say delta. Say delta. Now, also X being uh, sequentially compact, for any epsilon we can cover X by finitely many epsilon open balls. So has this we told above. So this is the first lemma, that if X is sequentially compact metrizable space, then for any epsilon positive, X can be covered by finitely many uh, open epsilon balls. Also, X can be covered by finitely finitely many open epsilon balls for any epsilon positive. So this epsilon is small but arbitrary. So what does this mean? This means um, we can pick point, say x1, x2, so on, xn and x, such that, so that is, there exists x1, x2 through x in x, such that we can cover this x by the balls centered at xi and radius epsilon, and this I varies from 1 to n. So that is what we mean by X to be covered by finitely many epsilon balls. Now, since this epsilon is arbitrary, we can take this epsilon to be equal to the delta by 3. So, in particular, take mm, epsilon to be equal to delta over 3. Then the union of these balls centered at xi and radius delta by 3. So this is equal to x. Now, since each delta by 3 ball has diameter 2 delta by 3, which is less than delta, by Lebesgue number lemma, for each I, there exists an open set in fancy A. So let us write this down here to get a better understanding. So since each delta 3 ball, now these balls have radius delta 3, so has diameter, so if this is the radius, so diameter is going to be equal to 2 delta over 3, 2 times the radius, and this number is less than delta. So by Lebesgue number property, by Lebesgue number lemma. For each I, so here we have I from 1 to n. So for each I, there exists an open set AI in the cover A such that the ball centered at xi and radius delta by 3 sits inside AI. So this is what Lebesgue number lemma says. So therefore, we can write X to be the union of these balls, since each ball is contained inside AI. So this is a subset of union of finitely many AIs. So, so what we proved here, we chose this script A to be an open cover of X, and we proved that there are finitely many elements in this fancy A which also cover X. So that means this X is compact. So hence this fancy A has a finite, I mean this fancy A exhibits a finite subcover of X, hence X is compact. Now one can note here, to prove third implies first, we use two lemmas here. One lemma is that if the space X is sequentially compact and metrizable, then X can be covered by finitely many epsilon balls. And the fact that if X is sequentially compact metrizable, then any open cover of A has a Lebesgue number.